Alrighty. So, for this section, we're going to go over MOS. I'm going to try to give you guys context on how to solve for MOSFET circuits. So, break this down to kind of lecture part, some maybe key example parts, and then some homework questions. I might just skip into homework sections instead of doing examples, but we'll see how it goes. Okay, for the lecture portion, I'm going to just show you guys a bigger context on the equations and the modes of MOSFETs. And we'll use NMOS as an example, but PMOS really is not too far away from it. And then I'm going to introduce this concept of small signal. And we're going to do a small signal model for a particular nonlinear system. That is the case, in this case, a MOSFET. Okay, and then maybe some examples. Maybe examples. All right, so that's the general premise. Let's begin. Okay, so for a NMOS, for a NMOS equation, we now have this nonlinear device called an NMOS or a MOSFET, and you can consider NMOS to be a three-terminal device. The three-terminal device consists of a drain, a source, and a gate. In my convention, the source is wherever the arrow is. I feel like for some reason different professors have different opinions, but yeah. I like the drawings where wherever the arrow is drawn, it's where the source is. If the arrow points away, from it, it's an NMOS, and if the arrow points into it, it's a PMOS.
Yeah.
This is the convention I like. So this is an example of an NMOS, and you just pay attention to the arrow for determining it. And you can see that an NMOS is a device with three terminals. And this is probably the first time you might have, well, no, besides an op-amp, this is the second time that you've seen a three-terminal device. Okay. So let's talk about kind of the structure of it. Okay. So the structure of an NMOS consists as follows. It consists of an N well, a P well, and N well. This is go back to some material science. We will not be here very long. And then we'll also have kind of this this gate. Okay. So let's call this the source. Let's call this the drain, and let's call this connection. The gate. Okay. So what happens here is that the P well is let's say more positively charged. The N well is more negatively charged. That is to say that electrons have a much easier time flowing in the N region, and holes or the lack of electrons have a lot easier time flowing in the P region. And right now, if I just have a MOSFET floating around, this P region, as you can see, is even right here is all positive still. However, if I suppose actually, let's take a look at what actually happens. This is also this is an oxide layer, so this is just non-conductive. This is just some kind of non-conductive layer. It's like rust, basically. And what happens here is that if there's no charges here on the gate, the electrons cannot flow. Why can't electrons flow? Because this area is right now positive, is better suited for holes to flow. Yeah. So the question is, how can I get, so in this default case, there is no connection from source to drain. There's no really tight or well connect. There's no tight or good connection there. Okay?
Yeah.
But meanwhile, if I apply some positive charge here, right? What happens to the positive charges here, or what gets attracted to this area?
They repel, and then you get negative charges.
Yes, exactly. The positive charges get repelled, and I start building up more negative charges here. And now the question is there a connection?
Yeah, there's a connection. Positive on the top and negative on the bottom.
Yeah, so from the negative side of the source to the drain, is there now a bridge that connects them?
Yes.
So can electrons flow?
Yes.
Correct. Electrons can flow. And you call this area here the inversion region. Why do you call it the inversion region? It's because it used to be PMOS, and now it's kind of because of a external voltage bias, I've inverted it to kind of be more negative.
Yeah.
Does that make sense?
Yes, it does.
So that's how things could flow. Now, let's say I just put, so let's say I put one charge. I put just one charge at the top, okay? Do you think that's enough to convince this thing to invert?
No, not one charge.
If I put one, I might just look like one, right? Is that enough to conduct a channel? Does one brick make a bridge? No.
No.
So, okay, so then if I don't apply enough gate, if I don't put enough charge on the gate, what happens? I do not have sufficient to conduct. So then what do you call the bare minimum? What do you think that's called? I meet a certain, what's the term? What's the English term that you guys think would be useful? If I need a certain amount, you call that a threshold.
Threshold.
Right? So there's a certain threshold of charge that I need to apply, right? Like the red is not enough. The blue meets the red is what you call cutoff. I am cut off from conducting. The blue meets the threshold. It's a certain threshold to conduct. But the question is it's like laying just the first plank across from one side to the bridge to the other. Can a single plank leading you as a bridge, can that like take the weight of like a car or take the weight of a huge amount of foot traffic? No, it cannot. So therefore, is it very easy to get energy or charge to flow through it? The answer is no. So what happens at the threshold? Yes, technically there's enough, right, to conduct, but there is not enough to conduct but there's not enough bandwidth or enough width on it to be able to allow for a huge amount of traffic or electron flow. So what do you say here? Do you think this bridge is easily saturated, or do you think it's relatively conductive at the threshold?
Saturated?
Yes, exactly. And that idea of saturation is what it's called. Basically, saturation is a function of what? Once I set the charges on the bridge, I lay down the brick. Now, saturation is kind of objective, right? Or sorry, subjective, because it depends on what? It depends on what is the foot traffic. For example, if I have to only conduct, let's say, 1 microamp, I don't need that much. But if I need to conduct, let's say, 1 amp of charge, that requires, I might saturate the road ahead of me. So that idea is called saturation. And that's why you have this mode of operation called saturation. So at saturation, it depends on the amount of foot traffic I'm trying to inject through it. And if I'm saturated, what happens? I am limited by what? What limits the flow of charge? What limits the flow of charge? It's the resistance of this guy. This guy is so resistive to flow that the voltage here will be very, very large. So in saturation, since the channel is so tight, the current causes a huge voltage drop from drain to source, or actually conventional current flows this way, sorry. If negative charge goes this way, conventional current goes this way, positive current, so to speak. And you can see at saturation, I have a very resistive channel. But if I keep on putting even more charge on it, if I keep on putting so much extra charge on it, what happens?
Becomes oversaturated?
Yes, and now what happens is that the bridge I have overbuilt. I have now built such an overbuilt bridge that it's so easy to get charged through this guy.
Becomes very small.
And this resistance becomes very small.
Yeah.
And what do you call that? That region is called triode. It's we could explain what triode means, but it basically just means you have a very low resistance channel. And remember, saturation and triode depend heavily on we need to define what they mean. But what can you see is that at different VGSs, as VGS goes upper and upper and upper, as VGS increases, there's a point, as I increase VGS, there's a point where I exceed VTH, right? Some threshold, or I am less than VTH, right? It starts off less than VTH, and this is called cutoff. And if I exceed VTH, I am on, but I'm either in saturation or I'm in triode. what determines whether or not I'm in saturation or triode? It depends on how much foot traffic am I trying to get through. But from a voltage perspective, I could define saturation. Or sorry, let's think about it another way. Under saturation, is the VDS high or low? If I have a saturated channel and I'm pushing current through and it's very resistive, is the VDS high or low?
It's high.
It's high. And so let's compare. So we're going to arbitrarily decide that you're in saturation when VDS is greater than VGS minus VTH. So do you see how when it's greater than a certain voltage, you consider saturated? And therefore,
Yeah.
what's triode? Triode is just the opposite way. When the VDS is so small compared to VGS minus VTH, we had to put some metric. We had to put some definition. So we choose to define against this. So when VDS is much smaller than this, what does that mean? It means that the channel has a very low voltage. So either I'm not pushing a lot of current through, so therefore this channel is not saturated, or or I'm pushing a fuck ton of current through, but the channel is not resistive at all. That VDS is very small. So basically, VDS small means resistive, very small resistance, and VDS big means that my channel is saturated. Does that make sense?
Yes, it does.
So do the names make intuitive sense now?
Yeah, they do. It makes a lot more sense.
All right. So these are the three main regions for a MOSFET, and the physics makes sense, correct? It's
Yeah.
just it's the example of just I start placing charge one by one. Okay. So what happens? What happens here in this graph? Let's say. So I'm going to call this my my VDS, and this is my IDS, right? And the first thing I'm going to say is let's set VGS equal to be less than VTH. So if VGS is less than VTH, what happens? Or VGS minus VTH is less than or equal to 0. What happens here? Does my VGS exceed the threshold?
No.
No. If I don't even exceed the threshold, what can I say about the channel? Can it
It's a-
conduct current?
No.
It cannot conduct current. So
So it's
IDS has to be
cutoff.
what?
0.
Yes, exactly. So this means IDS, this is cutoff, where this is 0 amps. Does that make sense?
Yeah, that does. That makes a lot of sense.
Okay. Next thought experiment. VGS equals VTH. What can we say about this example? I just barely turned on. That means my channel, do you think it's very easy to saturate or very hard to saturate?
Still very hard to saturate.
Sorry, one more time?
Very hard to saturate.
No. Saturate is, I just turned on the channel. You said build a bridge, I put a piece of straw. Do you think it's easy to saturate that bridge, or do you think it's hard to saturate that bridge?
Well, it'd be honestly.
No, it's gonna be easy.
because there's
Easy,
nothing
because the
there.
channel barely exists,
Yeah.
right? It's like I just made a website on my home like broken ass PC, right? And I said
Yeah.
like, can my website be saturated easily? Yes, because like it breaks at half a user, right?
Yeah.
Right.
So there's tons of room.
So sorry, what'd you say?
There's tons of room. It's easier to saturate.
No, yeah, it's incredibly no. Wait, what do you mean? There's tons of room.
Well, I mean, there's nothing there, so you can keep adding stuff to it, right? Is that what you mean when you say like?
No. When VGS equals VTH, what does the inverting region look like? It looks just like a very thin strip of negatives, right?
Yeah.
But what do those negatives do? They help like kind of like bucket deliver the energy from one side to the other, right?
But
Mhm.
the resistance is still pretty high that way.
The resistance is huge,
Yeah.
and the channel is saturated even at like a picoamp.
So yeah, I got it.
Does that make sense? So in other words, if I plot when I apply a very, very large voltage to it, do you think how much I get saturated? Basically, I get bar like if VGS equals VTH, I get barred. There's a horizontal bar basically says like you cannot cross this line because that's the limit of the channel, right? I build a bridge and this is the max limit that the channel can take. Does that make sense from a current perspective? Or does that need further explanation?
What I'm assuming is that you're saying that there could be a current flow.
It could be, but it's basically if you're right at the threshold, technically your limit is still zero. Like it's
It's still
infinitesimal.
it's still pretty hard.
It's infinitesimally small.
Yeah.
So approximately zero, but that's the limit,
Pretty
right?
hard to conduct current,
Yes,
but it
exactly.
is possible.
Exactly. It's possible, but it's like picoamp.
Yeah.
So it's basically zero in the infinitesimal case. Let's say let's try the next case, right? Let's try the next case where I have VGS is minus VTH is, let's say, equal to, let's arbitrarily say 1 volt, right? Then do you guys agree that, okay, I put 1 volt, I'm beyond threshold and now I'm at saturation, right? So what happens now?
Now we can conduct.
Now we can conduct, but the
Still-
bridge is still not super well built. So there's still a limit, right? There's a rated amount of people that could fit inside that bridge. So what do you say about the current? You expect the current to have its own some kind of limit, correct?
Yeah.
Like you cannot, there's no way for the current to ever exceed this line, right?
Yeah.
But at the beginning, so once I set VGS minus VTH, so what does this set? It sets the amount of charge basically on the gate relative to the source.
Yeah.
And then I start increasing the VDS. So at very, very high VDS, like let's say I put like 1 billion volts on this guy, no matter how much potential I apply to this guy, how much current can flow, whatever, and intuitively, what's the limit?
The bar,
That bar, right? So I have to start somewhere up here. If I apply, no matter how much potential, doesn't matter how much pressure you're trying to force through the straw, it just cannot do that flow, right?
Right.
But eventually, when VDS gets smaller, what happens? When I put only like 1 volt, and what happens to the channel when I stop saturating it? When I start asking for less demand, what will happen? Like, for example, if I put 0 voltage applied to this guy, what's the current through it?
0.
0. So 0 is a real point. What else? So if I increase the voltage slightly, am I saturated?
No.
And I conduct
No.
still a real amount of current, right? So it's approximately like a resistor here until
So
I
then
start getting until I get closer and closer to saturation. There's a curve.
yeah.
Does this make sense?
Yeah. Yeah. That would be the linear region, right? Where you're
And this is called the linear region.
Yeah.
And yeah, then we have a limit somewhere else. Okay, let's go to
Yeah.
the next case where let's say we have VGS minus VTH is equal to 5 volts. What do you think happens here?
now the resistance
Higher?
is smaller, then we can conduct current.
What happens to my saturation limit?
doesn't it get higher?
Power
It gets-
will be higher.
Yes, it's much higher, right? Because now I basically have like a 3 interstate, like I have a 3-lane interstate highway or something, right? But so and if I put infinite voltage, where do I have to sit?
You still
Eventually-
saturated.
At the limit. So
At
it's
the limit and at
not
0, and if I put 0 voltage on, even though the highway can deliver 1 billion cars in like a month, right? Let's say if I put no pressure on that highway, how many cars actually go through it? No voltage. If I put no voltage, how much current goes through it? 0, right?
Yeah, 0.
It's an empty highway. And then obviously as I increase it, it goes up. And then eventually I will hit its limit. Does this make sense?
Yes, it does.
All right. So does the VDS IDS curve make sense?
Yeah, and that would be the triode region, those 3 values. So that's essentially what's
No, this linear region here is the triode region.
yeah.
It's basically where VDS and VGS decides. So for me to find this limit, what do we need to find? I need a plot where VDS is equal to VGS minus VTH, right?
Yes.
Okay. And it turns out from experimental, we found that ID in saturation, you have 1/2 mu n COX W over L. These are all physical parameters times VGS minus VTH, right?
Yeah.
Squared. But I know at the limit between at the boundary between triode and saturation, I'm saying that VGS minus VTH is just equal to
VDS.
VDS. So I say ID sat is when the limit is when this is true. So what type of expression is this from IDS with respect to VDS? IDS as a function of VDS is just a quadratic, right? Times some constant K. Yes?
Yes.
So all I need to do in the VDS IDS graph is I just need to draw this dotted line that is just a square law. And this tells me, and this wherever it intersects, before it is triode and after it is saturation. Does that make sense?
Yes, it does.
So now does this graph make more sense to you guys?
Yes.
Yes.
Yes, it does.
All right. And intuitively, it makes sense, right? It's basically a goddamn, it's just, it's the stupidest idea. Just like from physics, it's like opposite charges repel, right? Like charges attract. And then you put the shit together and then you made a switch, right? It's like, it's like the silliest shit ever, but it's ingenious. And do you see how from this physical circuit, we could generate all of it? Like conceptually, we could walk through the trends of what it means to be saturated, what it means to be in triode, so on and so forth. Yes?
Yeah.
All right, beautiful, good job. So basically this area I will call triode. So anything left of this is triode, and everything after this, I am saturated. So when I say saturation, what is being saturated? In your own words, what is being saturated? The channel, exactly. So if it's easier for you, call it channel saturation. Either the MOSFET is operating in saturation, but you could put the word channel saturation, and that might help you guys remember what's actually physically happening. It's like, damn it, I would love to put more. It's like traffic. Basically, there is like bumper to bumper traffic inside the road. And that's what we mean by channel saturation or traffic saturation or roadway saturation. Okay. All right. So that's that's literally how MOSFET. It's called a field effect. A FET is a field effect transistor. Field effect just means field effect just means opposite charges reject each other. Opposite charges attract and like charges repel. And transistors, because you call this thing a transistor. So field effect transistors literally just takes advantage of the fact that opposite charges repel. Okay. Very good. All right. So now we have the physical model. Now that we have the physical model and related it, let's see what the equation. So now the harder thing is what are the actual equations that govern this, right? I need to somehow, I've made a MOSFET and I want to somehow understand. I want to understand how do you say? I want to understand what equations that govern this, or I could at least get modeling close to it, right? And here is your answers. These were what were found for NMOS device. Different people have slightly different models for saturation, but take a look. I don't like this definition I don't like these definitions. I have my own little definitions here. And they are more consistent with one another. So here, let me show you guys what I mean. Actually, you kind of already seen what I was doing. Okay. Okay. For cutoff, I prefer just to say that VGS minus VTH. VGS, VTH, to me, these guys are they stick together, okay? And then in this case, I just say it's less than 0. In linear, I say that VGS minus VTH obviously has to be greater than 0. Same with this guy. But for linear, VGS minus VTH is what compared to VDS? Or VDS compares to this number. In linear region, do you want VDS to be big or small?
Small?
Small. So in other words, you're saying that this has to be bigger than VDS, right?
Yes.
And in this case, VGS minus VTH in saturation, what happens is that
It's
it
bigger.
to be bigger. VDS is bigger. Does this make sense? So do you see how I love this? I hate this shit because it's so confusing.
Yeah.
I just use
Yeah, it
VGS
is.
minus VTH. In fact, I love VGS minus VTH so much that I just redefined this thing to be called VOV, which is V overdrive. It's the amount that VGS is beyond the threshold, right? If I say VOV is equal to 1 volt, what does that mean? I'm 1 volt overdriven beyond the threshold. that make sense?
Yeah, it does. Sorry about the noise.
No, it's okay. So I call this voltage overdrive, and I like VOV. So basically, I just think about I personally think about VOV. It's this to me a much more intuitive concept. Okay, so now that says so I don't whatever way you guys want to memorize or learn, this is just how I prefer to do it. To me, it means it's these equations are much more intuitive compared to what we just learned. Okay. Now let's take a look. In cutoff, how much current can you have? 0, right? So this checks out, right? Next is in saturation. I said that saturation follows almost the square law, where it's 1/2 mu n cox w over L. And then this is just VOV, this is just V overdrive squared. Now you have this extra term. This extra term in saturation, what did we say? Saturation, we imply that the channel cannot exceed the limit. In real life, if you keep putting 1 billion volts, eventually it will conduct. In fact, if I put 100 volts versus 1,000 volts, there will be a difference in current. Even though the highway you think has a limit, you know, if you keep on pushing it, it will slightly conduct. So actually, what happens here, guys, is that as the voltage increases, I will actually see a slight increase. I will see a slight increase in the voltage. And over here, I will see a slight increase. Oh, sorry, from a slight voltage increase, I will see a slight increase in the current. So in other words, this is just showing the fact that I can't just just because you're in saturation, you might imagine the highway is filled, but like obviously if someone aggressively drives down the highway and a bulldozer just pushes all the cars forward, it might not be the cleanest traffic situation, but technically you do increase traffic flow, right?
Yeah.
So yeah, so there is a slight slope to that, and this lambda factor you can imagine is very, very small. So basically, if lambda is 0, if lambda is 0, what's the slope of these lines? I go back to my saturation. Oh, sorry. If lambda is 0, this guy's removed, then it's just multiplied by 1, and you get back the flat lines.
Yeah.
Lambda is typically very, very, very small, and it's like this extra bonus factor from VDS.
So that's what zero biasing is?
Sorry, one more time?
And that's what zero biasing is?
What do you mean zero biasing?
I was looking at the notes and I was looking at that, but I mean, he didn't really use that big equation.
Is
Big
that
X
channel length
equation?
modulation?
Repeat?
Channel length modulation.
Yeah, this is called, if you want to know the actual thing that's happening, as the negative charges flow in a real scenario, when the negative charges flow, every single time I use something up, the channel actually gets thinner and thinner and thinner and thinner. And then even if the channel goes all the way here, right? This area here, even though it doesn't look like the channel goes all the way through, the distance here is small enough where charge can just kind of go through anyways. It can like not tunnel, but like it can force itself through the muddy water. And this is very resistive, and that's called channel length. This is it's like the effective length of this channel. As I increase this guy, it's getting the bigger the voltage I apply, it does actually change it. Like here, I imply that the gate charge is the only thing that affects the channel. No, as I apply as stuff really is moving. For example, your car does affect the road. It does wear it down a little bit. It does take some stuff off the road and stays in your car, right? Like this is not the only thing that affects the channel. So it's like kind of that effect, but yeah, you could say it's channel length modulation. See, it's all CLM. It's to do with the fact that as stuff actually moves or as you apply voltage through it, it does have a real impact on the channel itself. So this is called this is a channel length modulation term. Okay. Okay. So here are the equations. Oh yes, sorry.
Can you discuss about the pinch off too?
Discuss about what?
Pinch off.
Pinch off. Oh.
Channel pinch off.
Pinch off is just when you hit this point and then you're technically not conducting. Sorry. It's like when the threshold, it should be corresponding to threshold, I believe. If when the threshold just hits it, you just barely, the triangle barely reaches. That's my understanding. Is that not correct?
That's correct.
That's correct.
Okay. Yeah, that's about it. It's just like don't imagine the channel as a rectangle block. Imagine it as a triangle that tapers off as you get closer and closer to the drain.
Yeah, but there's something that makes the channel, that triangle smaller and smaller and smaller.
Yeah. It's the fact that it's like the Oregon Trail kind of idea. Because this is a P channel, right? The pluses here don't like being here. So
Yeah.
as every single time I move a charge through, they recombine.
Yeah.
And then and then it gets slightly more positive doped again.
Yeah. That's
Yes,
correct.
it's the boundary recombination.
Right.
Yes.
Mhm.
Does that make sense?
Yeah.
All right, very good.
That's correct.
So here are here are your equations, and the only thing I want you guys to take away is that they're nonlinear and you have some other effects. Okay. But for this linear region, it's modeled by a negative quadratic. So if you guys in the flat line model, the from here to here, it's actually just a second order polynomial. It's literally just a concave down and half of it. That's triode. That's how we model triode. And for this guy, we're modeling it. If channel length modulation is 0, it's literally just a flat line. It's literally like the highway limit, saturation limit. And if there is channel length modulation, you basically model it as because this is just a y offset slope on the VDS versus IDS versus VDS. Everything else is considered a constant. It's just y equals mx plus b. So this is just a line. So do you guys see how you have a quadratic and a line? Yeah.
Yes.
Okay. Yeah. So that's literally it. That's what the world decided on for MOSFETs. It's you measured the curves and we said, it's like a polynomial. And here you're like, it's like a line. That's it. That's the great modeling of MOSFETs. Okay. So, for IDS versus VDS. For IDS versus VGS, it follows the square law. For versus VGS or V overdrive, it follows the square law, where I get every single amount of voltage I apply, I get a square increase in the saturation limit. Okay, and those are mainly the equations. So let's talk about small signal model. So let's say in my MOSFET, unfortunately, these equations are nonlinear. These equations are nonlinear because you see squares of stuff. You see squares of VDS, you see squares of VGS, and yeah, not pretty. So there are two main voltages. There's VGS and there's VDS in the equation modeling. And also there's this ID, that's the current that flows through it. Okay. And I want to somehow remake this guy. I want to remake this guy as a linear component. So let's talk about this. And this guy is not linear because of these squares. So if I were to try to solve a circuit, like if I were to really try to solve a circuit like this, even with a resistor and a voltage source and a ground and an input VG, this circuit is not easy to solve because this whole thing's because of this nonlinearness of it. Like if VG is too small, I have a piecewise model as well. So the fact that it's piecewise, in other words, it has different behaviors at different bias conditions. At different conditions, I have different behaviors, which makes it incredibly nonlinear. So what can we do? Well, if I try to solve it, yes, I can solve it. It's annoying because I need to, depending on the conditions, I need to use different equations to model this guy. And that's not cool. That is not okay for me. If I want to kind of see how this device operates in the frequency domain. So in your previous course, I know that if I have a circuit of linear components, always generate linear differential equations. This is always true. So I could have voltage sources, I could have current sources, I could have resistors, I could have capacitors, I could have inductors, and I could also have voltage dependent currents, voltage dependent sources, and dependent current sources, right? All as long as my circuit's made of these guys, I am linear. Okay. So then you might ask me, okay, so how can and I know that a linear circuit will always give me linear differential equations, and linear differential equations can give me access to frequency domain analysis. System analysis. Okay. And my goal is to get here. But for me to get there in electrical engineering, I need to remake this guy looking like this. Does this motivation make sense? Or maybe I haven't explained it yet. Basically, the goal is I want frequency domain analysis.
Yeah, makes sense.
Okay. And you can agree that this MOSFET, it's piecewise, so it's piecewise, it's nonlinear, square-wise, it's nonlinear. So I'm kind of fucked, right? So what makes a component linear? Well, what makes a component linear is the fact that there's linear relationships between V as a function of I is linear. And that could be using derivatives, or it could just be a constant. Remember, a linear differential equation looks like something like this. Any linear equation will have this. It'll be an a bn dyn dt plus bn minus n dbn dy n minus 1 dn minus 1 t. Oh wait, no, wait. I wrote that wrong. The n should be here. See, my bad. Okay, wait, what? Okay, wait, hold on. Am I tripping? Hold on, give me a second. Where's it go? Yeah, it does go there. Okay, n minus 1 dt n minus 1 plus plus b1 dy dt plus b0 is equal to an dy dx and dt and plus plus a1 dx dt plus a naught. Yes, this is a constant coefficient linear differential equation. And I promise you, any circuit that has this will always have KVL, KCL, will always combine these guys linearly to generate an equation that looks like this, always. And from here, you get you could do the Laplace transform of it. And then you have Bn, Sn, Y plus blah, 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 whatever, right? You get the polynomials of S, An, Sn, X plus A naught, whatever, right? Plus B naught is equal to each other. I could solve this guy for now Y of S over X of S, which I call the transfer function H of S. And this guy is always going to be a ratio of polynomials, where it's always going to be an s to the n plus plus a naught, and bm or bn s to the n plus plus b naught. So it's a ratio of polynomials that gives me a transfer function, and then you get Bode plots and pose and zero analysis. So this is pose analysis, this is Bode, this is frequency domain analysis, this is also just basically transfer function analysis. So all that good stuff from EE 110, basically. So I want access to this. And the problem is that this thing is not going to be linear. This thing cannot generate this type of circuit. And you can see linear means that even differentiation. So that's why capacitors are considered linear, because it's equal to I equal to C dV dt. As long as I have a current voltage relationship that follows this form, even the differentiations of it, it's still linear. An inductor, V is equal to L di dt, is still linear because the inductor and the capacitors are constants. V is equal to IR is linear because V and the I are related by a constant R, and so on and so forth. So I just want to make this guy as a set of this, and we're done. Does this make sense?
Yeah.
Good. So how does one do it? I have all these guys behave in a linear sense. And let me explain what I mean by a linear sense. So in this guy, for example, let's pretend I wanted to know this guy clearly is not linear. First off, it's let's look at the red curve. Let's operate on the red curve. So let's say I want to operate here. So it's basically flat, then it's on, then it's flat, right? Awful, right? So it's not linear, non-linear, I mean, it's piecewise just awful. So let's say, hey, Eric, I know I operate in saturation, and I know that my VDS is going to have some perturbation. So here's VDS not. Here's VDS nominal plus a small VDS perturbation. So the VDS perturbation is going to look like so let's say my circuit at DC is just operating at this condition. Like you solve this guy using the nonlinear clusterfuck. But at the end of the day, you will determine that, okay, this is the voltage here, this is the voltage here, here's the data, and that establishes baseline, the nominal operating condition. Once you've established a nominal operating condition, you can tell me which mode of operation you're in. And let's pretend this guy's operating at this point here. This is my operation point, op point. Okay? Any questions there? Like you solve this circuit using the large signal model, and you found its operation point. So I know that my circuit's operating at, let's say, this VDS at this output current with some VGS. Do you guys agree that it could be possible to get there?
Yes.
Okay. Once you add that op point, I want to because this thing is non-linear, there's nothing I can do to make it. I cannot make this whole circuit across the whole operating range. I cannot make this whole thing that is inherently non-linear linear. However, I could declare that a local region around it can be linear. This I can say. So I'm saying that, okay, as long as if I'm operating here, if I'm operating at this op point, wait, hold on. Why are my lines tilted? If I'm operating at this op point, locally, as long as my input parameter is within this small perturbation bounds, then the output will look like a linear relationship. So basically, when my input voltage swings down here, it corresponds to me being here. So this point and this point are the same. When my input is here, my output is going to be here. When my input's up here, my output's going to be up here. And if I plot these guys, I should get back. If I put in a sine wave, I get out a sine wave. Do you guys agree? Or does this idea make sense?
Yes.
Yeah,
I'm
no, it
good.
makes
Thank you.
sense. That's kind of what we did in lecture two.
Exactly. So this is what you say. So can this MOSFET ever be globally linear? Globally linear. Is it possible?
No, but it can operate on a linear point.
But you can choose an operating point and say locally I am linear. And from derivatives, you know that any function, as long as you zoom in enough, it's always locally linear. Does that make sense?
Yes, it does.
So I could choose any function and it's locally linear. Now, so when does this model? So as long as I take its local derivative, I can find the effective gain from like the relationship between V and I. Like here's, if I take a local derivative, what's the units of the derivative? What are the units of the derivative? It's in units of IDS of ID per VDS. Yes, that's the
Yeah.
slope.
Yeah.
And that means that, and then I get a constant K, right? Does this constant K not tell me the relationship between ID and VDS? Just like a resistor? Or in this case, a transconductor? Does this make sense?
Yeah, no, yeah, it does.
It tells me a gain, right? So all I'm doing is that I just need to find its local operating points. And that's why for each of these mode of operations, right? For each of these mode of operations, each one of these guys will have their own definitions. So let's say I make a MOSFET. Let's say I make a MOSFET. And I said there are two key parameters. There are three key parameters I want to find, right? There are three key parameters I want to find, and they are VGS, VDS, IDS. I just need to find the relationship between them. And what you see is that inherently all these guys are functions of it's the Y function happens to be IDS typically. The Y function happens to be IDS. So in other words, I have things as a function. I have IDS as a function of the other parameters. So I have IDS as a function of VDS and VGS. Do you guys agree? That's at each single one. This is a function. IDS is a function of VDS. IDS is a function of VDS, VGS. IDS is a function of VDS, VGS. Do you guys agree?
Yeah.
Okay. So for each mode of operation, I could define the following. I'm trying to decompose this guy into this. And I have two options. What are the two derivatives I can measure?
IDS and VDS?
Okay, IDS to VDS, right? Good. What else? What else can I take a derivative of?
IDS, BGS.
Yeah.
Correct. And those are your only options, right?
Yeah.
Now, if this says that, hey, a perturbation in the current causes a perturbation of the voltage on the exact same nets. So I have a drain net and I have a source net, right? And I say if I perturbate the voltage, I get a change in current. What does that remind you of? If I perturbate the voltage across it, it causes a change in the current.
So it's kind of like a
The
MOSFET.
voltage drop.
Wait, what? What'd you say?
Also,
What do you mean by that
Perturbate?
word? Yeah, what do you mean by that?
Perturbate just means like if I did this is called a perturbation around the operating point.
Oh,
So perturbation just means like you know those
Yeah,
toys with
yeah.
like the balls?
yeah, I get it. I
Yeah,
get it now.
perturbation is like bringing it up slightly and then letting it flick back and forth.
yeah.
Yeah. So you have a voltage drop in that.
I have a voltage drop here and the current goes through it, right?
Yeah,
So what component does this define?
a load.
Resistor.
A resistor. Now, unfortunately, it doesn't have units of resistance. So let's say I invert this guy, and now I have an RDS term, right? And I use a lowercase r because I assume I use lowercase r because I assume locally a small signal is applied, a perturbation or a small signal is applied. I can call this RDS because it tells me how the current through IDS changes as voltage of ID. The nets are the same. The current through this is IDS current and this is the VDS voltage, right? If a voltage across two nodes causes a current change between those exact same nodes, that's a resistor, isn't it?
Yeah,
Okay. And in this case, if I change in voltage from VGS, so here I have a VGS way over here, right? And it causes an IDS change. What does this guy look like? What kind of device is this? It's a voltage source that controls a current, but they are different areas of the circuit. What do I draw?
Can you repeat that?
I'm out of your selection of these devices, what do I draw?
you would draw voltage.
What's the output? What's the thing that's being controlled?
VG.
No. The bottom
Current is
Voltage current source.
voltage controlled current source.
a voltage controlled current. Okay, from derivatives, you guys remember? I want to know how Y changes as my input X does. So the input is at the bottom. So someone said it correctly. It's The thing that my controller is in what units? It's a voltage source, or it's a voltage, and the thing that I'm outputting is a current. So it's a current source, a voltage controlled current source, which looks like this, right?
Right.
So I have a current going down here, right? That's a function of this voltage. And I'll call this guy, what units is this guy? This guy has units of transconductance. So I'm just going to call it G MOSFET. Yeah, so this guy has this current dependent current source has this. It's GM times VGS tells me the IDS through this guy. Yes? Does this make sense?
Yeah,
Maybe?
yeah,
So basically, I've now made
that makes a lot of sense.
as long as my MOS. So basically, I could take my MOSFET, which is this annoying ass circuit, and I can translate it to what? I have a gate voltage, I have a drain voltage, and I have a source voltage. And here is where VGS lives. VGS lives right here. And here's where VDS lives. And what can I say? If my functions only have the only options I have are two things: the derivative with respect to ds and the derivative with respect to gs. For the derivative with respect to v from IDS VDS, and I invert it, it now has units of resistance, right? RDS. And most places they call, and I draw a resistor from drain to source, and I call it actually instead of RDS, you call it RO in this case from convention. RO. And what about the other case? Is that that's one derivative. The other derivative says I have VGS changing VIDS. And we just agreed that it's a. When I take its derivative, what circuit element do I model it by? This voltage controlled current source. And its gain is GM-VGS. You guys agree now? Do you guys
Sorry
see
to
where
be
these two
annoying, but can you on the left hand side for VGS plus and minus? No, on the one that we redrawing. Yeah, where did that come from again?
when you define this voltage control current source,
Yeah.
it relies on VGS, so I
Yeah.
need to define VGS somewhere in the circuit, otherwise it
Yeah.
doesn't work.
Where's VGS on the circuit on the right? Oh, I got it. Never mind. I got it.
Yeah. Does that make sense?
Yeah.
So do you guys agree? If the equations are this, I take all the possible derivatives I can, and I only have two possibilities. For each derivative, I make a component. Every derivative I take generates a component. One of them happens to be a resistor. The other one happens to be a voltage control current source. And there's no other option. Does this make sense?
Yeah, it does.
So,
That helps so much.
So do you guys see if you have, so you could take this philosophy, if I give you any system of nonlinear equations, you can always systematically relinearize it by taking all the differentiations possible and making it into a component. Does that make sense?
Yeah.
This is applicable to any nonlinear system. It just happened we happen to be looking at a MOSFET today. Okay.
I was having trouble understanding the RDS until you made it simple right there. That honestly helps so much.
Yeah. So do you guys have any questions about how we generate the small signal model? And there are two. So there are
But I have
two.
a question.
Yes.
So when we are considering CLM, we have R naught, right?
Oh yeah. We'll get there. So first off, these derivatives. So what is the definition of GM? GM, we're going to define it to be what?
GM is the
Conductance of
One more time.
GM is IDS over VGS.
The derivative.
Yeah, derivative of it.
Okay. And what is R naught defined to be?
VDS over IDS.
If you do it that way, the differentiation, if you did that way, you have to then invert this guy, invert.
Oh, yeah.
them.
So yeah.
So do DIDS over DVDS and then invert the final result.
Right.
That's
Yeah.
easier.
Yeah.
Okay. So do you see? So how many? So to generate two components, I need to take two derivatives, right? And these derivatives are acting literally here. Like you're finding the slopes at different points, right? So over here, what can you say? Which region of operation am I in? In this operation condition.
Saturation?
I'm in saturation. So which ones did I derive? I took this one from saturation.
Yeah.
And then I get, so do you see that each one of these modes of operation, each of them have their own GMRO equations?
Yeah,
how
I
does-
just have to be wary of it.
Exactly. Does that make sense, guys?
Yeah, that made a lot more sense. I was having trouble with this exact concept.
Yep, no problem. Yeah. This is very hard to explain. So every single region, because basically I'm taking, because if I take a derivative here, why the fuck am I using the equation here, right?
Yeah.
Right. So
It
help me
makes
out here.
sense.
In this case, what's GM and RO? If IDS is equal to 0, if the function of IDS is equal to 0, what's this derivative equal to? And what's this derivative equal to? What's GM equal to?
Just zero?
I think
And what's
it's
RO equal to?
Zero also?
No. Do the derivative, you get 0, invert it.
Infinity.
Oh, infinity.
Infinity.
Right.
In other words, this is an open circuit and this is open circuit because 0 GM0 means that this guy is a current of 0, which means open circuit, open circuit. In other words, the small signal model looks like gate, drain, source, and that's it. Everything open circuit. It's just 3 nets sitting there. Agreed? Yes. Does the cutoff region make sense?
Yeah, it does.
So this small signal model is not unique to saturation, triode, or cutoff. You draw the same goddamn circuit no matter what. It's just how do you get the two key component variables, GM and R naught? How do you evaluate numerically these two? That depends on your region of operation.
Right.
Does that make sense?
Yeah.
All right. So in these GMR, so one of the question was RO here. Okay. So let's say let's derive this guy with respect to RO. So this is equal to K V overdrive squared 1 plus lambda VDS. Yes? Yes, this is the yes, this is the request. Okay. So if I do R naught here, right? Let's get R naught. So that's dIDS over dVDS inverse. So let me just calculate this guy first and then take its inverse. So if the IDS is equal to this, what is the coefficient of this guy? It's just
1
K VOV squared is just this is just a constant, right? Lambda VDS. Would you guys agree?
Yeah.
Okay.
Maybe.
And then I invert this guy, right? Then I need to invert this guy. So that's equal to 1 over K VOV squared, lambda VDS, yes? And this is equal to R naught, yes?
Yes.
So here, and then K VOV squared is approximately just IDS. Like you assume that this is the dominating factor. So let approximate is IDS. And then you have lambda IDS. Oh yeah, sure. There should not
Yeah,
be.
plus.
I don't know why you guys trusted me.
No, I just figured you'd get rid of that one.
Yeah. My bad. Yeah, you take the derivative, so only the lambda pops up. So do you guys see how you get the expression R naught is equal to lambda ID 1 over lambda IDS? Yes.
Yes.
So here the answer is 1 over lambda IDS is a very good estimate of this. And when lambda is equal to 0, what does that mean? It means R naught is,
Infinity.
and therefore so when you say no channel length modulation, then lambda is equal to 0, then therefore R naught is equal to infinity, and therefore this component just does not exist there.
Okay, makes sense.
Does that make sense?
Yeah, that does.
So for each one of these guys, question 1 and 2 in the homework ask you to kind of derive them, find expressions for them, and they can be very. The trial ones are very ugly. Just do the math. GM you can kind of solve, and we did those 3 examples. Like there's the three ones that we have done together. In your guys's notes. I think this is it, right? And these three definitions are only applicable where?
Looks like they're applicable on saturation, I believe.
Yeah, the saturation.
Only saturation. Okay. These have their own equations. You guys got that?
Yeah.
So what's
I wish you would have made a table for us. But
yeah, we can work on a table. Or okay, so
you have one, I think. Yeah.
so what's happening here is that I have you have a MOSFET, right? Here's the storyline so far. We have a MOSFET, and then we realize it has we have a what you call large signal, or basically the equations. Large signal equations, and it has three modes of operations of cutoff, triode, and saturation. Yes?
Yeah.
Okay. And you need the large signal model to figure out what's the key thing you need to figure out once you get a general purpose MOSFET circuit. Once you have a MOSFET circuit, you use the large signal equation, and what do you get? What's the key thing you need to find before you go into small signal? You need to know what, guys? What do you need to know?
Yeah.
Okay, fine. Let's say we have the circuit. I said, get me the small signal model. Okay, what's your first objective? You have the equation, you have all these equations, and you have this guy, and I tell you like this is 1 kilo ohm, whatever, right?
Yeah.
Okay, what do you need to do to get the small signal model?
You need to you need to set it up.
Sure, you set it up, you solve, and what's the key thing I'm solving for first?
See if there's in saturation, linear, or
Yes, and you call that the operation point.
Yep.
You need to find the operation point. Also, notice the derivative itself relies on the large signal. Like I need to know the nominal. These are the nominal VGS, VTHs, and IDs. Like this is the operating point. These are all up point. These are all up point. Defined. Like the slope of this line is very different depending on what my actual VGS, VDS. Like I need my IDS naught, VDS naught, and VGS naught. So operation point is IDS naught, IDS naught, VGS naught, and VDS naught. The operation point is defined by all three of these. Does that make sense? Like this is the point in which my circuit is operating at, and then I'm going to put a perturbation around it. Does this make sense?
Yes.
And because why do you need these? Because once you do this, what are the two components that you need to find for small signal? You need to find
R naught and gain.
GM. And so you need to know these three because it tells you also the operation mode, the mode of operation. And from these together, you know which equations are used and what do you plug into those equations to get GM and R naught. Does this logic tree make sense?
Yes.
So how do large signal and small signal communicate? You need to know all of its op point for every MOSFET. That's the handshake between the two worlds. Does this make sense, guys?
yeah.
All right, perfect. All right, that's the lecture portion of this. We could jump into some problems now. Okay, so is there a particular problem you guys want to look at?
Do you mind just like not solve the problems like for homework 2, but like for the first 4 problems, maybe like just talk about it a little bit, just like a quick
I can extend this thing for another 45 minutes. I don't if you guys are comfortable. I'll give you guys some more time.
Well, yeah, that'll be great. If you don't
Yeah,
mind.
lecture went longer than I expected. So given that, do you guys have anything you guys want to look at more in depth?
Well, I mean, people can decide as well.
Or do you still I could still tackle what you just asked me to do. Let me just
It's just solving like the first 4 problems using the lectures. Yeah, we can solve them, but like not sure if everybody feels like this, but really understanding what's happening, it's a different
Yes, agreed.
So
And I
not
don't
solving the problem, but just talk about it, like the
I don't think he wants anything specifically solved either. Like from what I was reading in the homework, just kind of like setting it up. You know what I mean? Like correctly, like coming in at the term, setting it up.
Here. So here. So let me pop your guys' homework open again. And okay, so you want to look at the first 4 questions?
yeah, if you don't mind.
Okay. So compute the transconductance. Transconductance is which term?
GM.
Correct. Transconductance is GM of a MOSFET operating in the trial region. So what are they asking you to do? They're asking you, GM is defined to be what again? Someone tell me?
Derivative ID over VG, derivative of VG, and then we
Correct.
take the derivative of ID with respect to VGS, right?
Correct. Okay, so it was here too. So, and they said in the trial region. So which equation are we taking?
We are going to take
What? 1, 2, or 3?
the trial is the ID is equal to mu n.
It's the
Yeah,
lead one.
Right. So we just want to take its derivative. Okay, so let's find the derivative.
we ignore the lambda VDS. And
Yes. Let's ignore this. Yes.
And the assumption is because it's really small, right? That's
Yeah. Let's just assume that for now.
right.
Okay. So we do GM derivative with respect to VGS. Okay. So I'm just gonna call this guy. I'm just gonna rewrite this guy as K.
Okay.
I'm gonna call this VOV. VOV times VDS minus VDS squared over 2. Yes?
VOV is VGS minus VT, right?
By my definition, yes.
Gotcha.
Okay, so let's solve this guy. So the derivative is just the constant K stays there. The derivative of the first term is going to just be VOV.
Yeah.
The derivative of the second term is just going to be minus VDS because the 2 comes down and cancels out. Yes?
Yep, that's correct.
Okay. And the answer is just this. Done. Okay. That's GM.
And then we are told that VDS is 0 and VGM is 0. We need to explain why, right?
Explain GM is equal to 0 for VDS. So they want to know GM is equal to what when VDS is equal to 0.
VDS is equal to 0, yep.
Okay. So in this case, for VDS equal to 0. Wait, why GM is equal to 0?
Yeah.
So my thought was like not derivating it, but just plugging it in there.
No, I know. It's not going to work. So hold on. So
Okay.
VOV is
That is why I was asking, because I thought of
no, this should be R naught.
I thought of also plugging it in, and that actually gives you 0, but that actually makes no like.
No, hold on. Minus VDS. VDS is equal to 0, right? So isn't this just still? This is just still K VGS minus VTH, isn't it? What are they saying here? Define GM to be this. Okay.
Does
Do you
GM
see? Do you see your equation on the right when you call the first portion of it K and then the
Yeah.
VDS? Okay, so you have that. In that case, if VDS is 0, then that
IDS
times
is 0.
VOV is going to be just 0 times K 0 minus VDS 0 square over 2 is just 0.
No. Because this. No. That's not how derivatives work. This guy should look like this, right? And it's
Yeah.
only applicable
Yeah,
from here to here,
exactly.
but
Yeah.
then technically it extends downward, doesn't it?
Yeah.
And this also extends down. It's a parabola.
Yeah,
But
exactly.
this is the only between these 2 points are the only thing that's exposed in this
Mhm.
like operation world, right? So and it's saying that okay, and let's say this is let's say that this graph here is VDS IDS. IDS VDS, right?
Yep.
if VDS is equal to
0.
0, then you're saying
Then IDS is 0.
I know, but yeah, you're finding this point, but the question is GM is the derivative here. So if I take the derivative but in the real curve, it's flat, it goes up, and then it stays flat again-ish, right? For saturation, right? This is the red curve is the real MOSFET. And then the blue parabola is just this triode region portion
Yeah.
of it, right? And you're saying, and then if I take this and if this is my operating point and this is my slope, I have two options. Either for the real MOSFET, either I take the red and then there's a real positive slope, or there's or I take the left-hand side to which the slope would be 0. So I'm saying if right now we took a derivative coming in from the right-hand side, right? This derivative we took using this equation, which is coming in from the right-hand side, which does give us a real positive slope. So I do expect this. I just don't. Honestly, okay, is there a solution key? Because I actually don't agree.
No, I'll send it to you later. We'll get one tonight. But
Yeah.
honestly, I think essentially what you did with the first step, the first 3 questions, honestly, I think you're right with the GM equals K, V, what is that, V naught?
VOV?
Yeah, VOV minus, I think that's right. And then to explain it,
But no,
honestly,
I'm saying this is not true.
Yeah, that's what I was like.
That's what I was thinking, and then like
But
yeah,
it's
I
from the book.
plugged that
It's-
thing in the IDS by VDS, and then like plugged 0
It's
in
on the
there, and
book,
then
so
found GM
that's
equals-
why for me it was
Yeah,
hard to
no.
question it.
This is
But
not true.
technically, that's not what GM is, because
Eric.
GM is the partial derivative of ID over DVGS, so it doesn't make sense.
If you once you derive it, don't you have an equation where it goes KVDS? GM equals KVDS. If
So
you
if we take this guy, maybe I need to consider this guy. No. That's not true either. Because
oh, wait a
this-
minute, hold
the
up.
VGS.
Hey, did you guys give him if you look at that problem and you look at, there's extra, what is it? Like, so it says right here, assume in the following problems, unless otherwise stated, assume.
this
Yeah, is that,
That's just giving you values for
that just gives me values for K.
for
Yeah,
K and
sounds nice.
BTH and yeah. That's
Yeah.
like we can plug in those values, I guess, but that doesn't
No, yeah,
it doesn't give us GM equals 0 VDS.
I disagree. I still.
I wonder if
disagree.
the question the question that they're asking is explain why
like for the
GM does
specific
not
point.
equal 0 and VDS is not equal 0. That could be more of a
Yeah,
question.
someone get the solutions. It's a textbook. It has a star. I think it has solutions somewhere. But I fundamentally disagree with it.
There's
Okay.
a solution for this book.
I don't know. Maybe.
Let me find
Hey.
it.
I'm looking
Hey.
it up.
I'm gonna go to the next problem because sorry. Yeah, I disagree with it.
Thanks, anyways. That's
Yeah.
I was asking because I was also feeling the same way.
Okay, so here they want art. Yeah, exactly. So they said use this as a definition of this, and then we want to find its equation. Yes.
Yeah.
Yeah, I think so.
Okay, so we take this guy. We take this equation, and we solve for it, right? So we're going to inverse whatever's inside this guy, and the derivative with respect to VDS. Oh, we're
We took the derivative.
Jesus Christ. Yeah. What the fuck did I do? You guys trust me way too much. GF is the derivative of VGS. VGS is inside here. Oh, Jesus, right? So this is K. VGS is inside VOV. It's just gonna pop out the. I'm just gonna get the. This is just a constant. Oh yeah, shit, it is right. Oh shit, guys. Yeah, never mind. Yeah, shit, dude. We fucked up. We fucked up hard. All right, it's K.
Yes.
So, yeah, it's VGS. So take the derivative of this. So
the
I get
equation.
VDS here, and everything else is 0. Yes, this is the answer. Yes? If I just take this guy's derivative, or sorry, take this guy's derivative, you get the
I'm
K.
taking the state of VGS, right? That's
Yeah,
why.
so VDS distributes, right? And so I only get VDS back out. Would you guys agree? And this
Yes,
guy goes to 0?
yes.
Ah, shit, dude. Yeah, of course. Oh my god. GM is equal to 0. GM with VDS is equal to 0. I agree with the textbook suddenly. Yes?
Yeah.
And what is it saying? It's not the slope here. No, 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 no. This is the slope of IDS to VDS. That's not, this is the wrong slope. The slope is that when VGS. Oh wait, when VDS is 0, it doesn't matter what VGS is, right?
Your
Because I'm
graph
not
is-
putting any
also your
voltage
graph
here.
is VDS and VDS.
Yeah. Sorry. Okay, yeah, this makes sense. And you guys have any? Yeah. So my intuitive explanation is that without VDS bias voltage,
There is no
there will never
ID.
be any ID, right?
Yeah.
Therefore, VGS, there we never, no matter how VGS changes, right? Yes, does that make sense?
It makes a lot of sense. You're good.
Okay, yeah, sorry, Jesus.
Thanks.
Now we do the derivative that we just did, which is obviously K times this, right? And we just invert the guy and we're done. Would you guys agree? Now I'm derivating with respect to VDS, so now I get this thing. Yes? Are we okay with this?
Yes.
Yeah.
All right. So now we have finished the table. Let me make you guys a table. Damn it, I wish there was a more beautiful. Okay, here. Fine. You
Hey,
guys.
Eric, I have a question
Yes.
regarding the equations for the NMOS.
Yes.
Are they is the PMOS equations the same as the NMOS?
No, kind of.
Isn't the saturation equations and stuff like those ones the same, but essentially the values like like greater than, equal to, or less than is different. Like it's just flip flop.
That's not how I would recommend. I don't know. That's not how I know it. Like, I just here. Every time you see VGS and VDS, I put an absolute value and I let my logical reasoning on the relative value. Basically, can we talk about PMOS later?
Yeah, no, we'll do it later.
Yeah,
I think
yeah,
I think I put notes.
There's
of the,
I am not a fan of memorization. I like once we build a foundation, I want to preserve the foundation, and I'll restructure PMOS I will force PMOS to use the same equations. And the only thing I have to add to it is add on this other intuitively logical step, which follows this basic understanding here. So yeah, we'll talk about PMOS after, but let me make you guys that table then. Okay, so we have the regions. No, we have the modes of operation. We have your criteria. You have your equations, your IDS equations. Then we also need your GM and RO equations, and we are done, right? So the first region is going to be cut off. Okay, the criteria is what? Anyone want to help me?
Equals to 0.
No,
plus than.
Oh,
Greater
yes,
than.
it's less than 0, right? Less than or equal to 0, yes?
so that
Yeah.
VGS equals to ETH.
Okay, what's IDS is equal to?
0.
Yes. GM is equal to?
Same, 0.
Yep. And RNO is equal to?
0.
Nope.
Infinity.
Yes.
1 over idea, yeah. 1 over lambda IDS, right? That's why it's infinity.
No, no. Oh, 1 over lambda IDS is for which mode of operation?
That's for linear and saturation.
Incorrect. It's only for one of them.
For saturation?
Saturation. We
Okay.
just found what R naught is for trial, didn't we?
Yeah, we did.
Right? Every operation mode has their own sets of equation. That's the key takeaway.
Oh, I'm so glad we get a note sheet.
Okay, so triode. What's the criteria?
Is greater than 0.
And also, VGS minus VTH is
Less
what?
than 0.
Less than.
Triode.
Oh, it's
Oh,
also
wait,
greater
greater.
than?
I want VDS to be small as possible, right? Because it's super, yeah?
Yeah.
Okay. Here, there we go. Yeah. Ah, shit. Give me a second.
Yeah, a phone call. Kathy Knappy?
Okay. What is GM in this case? In the trial region, we just found GM to be KVDS. Yes?
Yeah.
And R naught, we just found to be
iPhone 14, right? Pro?
1 over lambda, 1 over K VOV minus VDS. Yes? Okay, last one is saturation. What's the criteria?
Is it
Greater than or equals to 0. VGS minus VTH is less than or equal to VDS.
Yes, VDS is large because my channel is saturated, so there's a lot of traffic. Okay. Equation. Okay. GM is equal to a whole bunch of shit, right? But the one that I think you guys are maybe most likely to use is this one. If you as long as you have ID, it's pretty good. 2 mu n cox w over L ID. Okay, and R naught is equal to 1 over lambda ID. Yes. Okay. So so the reason why the cutoff is infinite is because the derivative is actually 0 no matter what it is. And therefore the inverse of that for the resistance is infinite because 1 divided by 0 is infinity-ish. Yes, does this table make sense?
Yes.
All right. Here's your guys' cheat sheet for that table. Okay, we continue. Okay. What other questions do you guys want to do? Want to just keep going?
I think Josh had like maybe like 2 that he wanted to look at.
7.7 and 17.7 and 17.28.
Sorry, can I see the table one more time?
Oh
Oh,
yes.
he's gonna post it up.
Wait, are you just if you're gonna take a screenshot, I'll just yeah, everything gets posted. You don't have to waste your time screenshotting.
Got it.
You can do others as well, no worry. I leave it up to you guys. What do you guys want to do? All right,
You
you
need
know,
17.7. Okay.
17.7?
Yeah, 17.7.
We wish to design a stage in figure 0.86, blah, 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 with a drain current. So the target is what? ID equal to
0.5.
0.5 milliamps. I'm using uppercase to indicate large signal or like the operating condition. Okay. If W over L is equal to 50 divided by 0.18, calculate the value of R1 and R2 so that these resistors carry a current equal to 1/10 of ID. So I want the current in R1, which is equal to the current in R2, which is equal to 1/10 of ID, which we can solve for right now, right? This is 0.05 milliamps. Would you guys agree?
Yes, it is. Yep.
Okay.
That's what I did.
This is an NMOS or a PMOS?
It's a NMOS.
Correct. And can you label which one? Where's the source? Where's the gate? Where's the drain?
Source is below the M, drain is above the M, and then gate is between that node. Yeah.
The gate's the gate. Yeah. Okay, good. Yep. The source is where the arrow is. Very good. Okay. Okay. So then if it's an NMOS, I just want to solve for K, which is equal to mu N COX W over L. So for this problem, I'm just going to pull from here. So mu N COX is just 200 micro amps per volt squared. W over L is this nice clean 50 divided by 0.18. We can just solve for this K value. Or, yeah, we can solve for this K value. 200 micro times 50 divided by 0.18. Okay, 0.5. Okay, there we go. Okay. Okay. Okay, that's K. Very good. It has the correct units of amps and volts. So as long as I make everything amps and volts, we're okay. Okay, and yeah. So we wish to design this. So it says find the values of R1, R2. Okay. So what needs to be true? If I how much current goes into the gate? You guys know?
Isn't it?
Zero. It's high
Zero.
impedance. It's zero. It's always zero. Yeah, IG is always zero. So the current through R1 and R2 is the same, right?
Yeah. It's
They have to be the same because there's no loss of current this way. So in other words, I need to design this such that so if I know the current through these guys, I know that VD, the voltage on the drain, is the voltage across both resistors. So I know that VD is equal to the current through them times R1 plus R2. Do you guys agree? This voltage times the current through it is equal to the resistors added up. Would you guys agree?
Yes.
All right. So we have this, and we have now expression for VD. And also for the expression of VD, do I know how much current is going down this path?
Yeah, because we know the VDD and we know the ohms. Two.
Yeah. How much current goes down this path? Actually,
Isn't it times the 2K, the resistance?
nope.
And then
Nope. So I think
How
it's 0.5 plus the current going through R1, which will
Correct.
be 0.05.
Correct.
0.5 plus 0.
Because you know this current here, you know the current this way, right? So we just do KCL here. Would you guys agree?
Yeah.
So the I and the 2K resistor is that much. So
Right.
VD is also equal to what? VD is also equal to VDD minus the I 2 kilo ohm resistor times the R2K resistor, yes?
Right.
Which is equal to 1.8 minus 0.55 milliamps times 2K, 2 kilo ohms. So 1.8 minus 0.55 times 2.
Do we have to do both resistors or just that one?
Both.
What do you mean both resistors?
R1 and R2, or is it
You mean
just?
add up the currents? These currents are in series, right? If you do KVL here,
Yeah.
KVL
Okay.
here,
So you did it. Okay.
it's the current here, which is the 0.5 milliamps,
Yeah.
and the current here is 1/10 of that. Yes.
Yes.
So I get 0.7 volts on VD. Yes?
Yep.
So therefore, from here, I can now say that R1 plus R2 is equal to, I know the current here and I know the voltage here. So VD is 0.7 and the current R1, R2, oh, sorry, the current there is 0.05 milliamps. So this is now going to be 0.7 divided by 0.05, which is 14 kilo ohms. You guys have any questions so far about how I get R1 plus R2? And now I know the voltage VDS, and now I know the voltage VDS. And I just need to find the voltage VGS. Any questions so far?
No.
Okay, so now I need to find, so now I have this total, I now have the total resistance. I just need to find the volt. This is going to be a voltage divider from this being 0.7 volts here. And I just need to figure out what VG needs to be to get a current of this much. So, and because, and what do you know to be true? Am I in saturation? We have to assume something. I'm going to assume we're in saturation first, because saturation is typically easier to handle. Okay.
Mhm.
So I'm going to assuming saturation. I have the equation that ID is equal to 1/2 K VGS minus VTH squared. And I'm going to have no channel length modulation. Okay. I don't have channel length modulation because they don't really mention it.
Oh, it said you can assume lambda equals to 0 there.
Oh, okay. That's even better. Okay. So if this is true, I know that ID, I know K, and I know VTH. So can I just solve
You
for
can.
VGS?
Mhm.
Would you guys agree?
Yes. Yeah.
Okay. So this guy is going to be equal to 2 times the square root of 0.5 milli divided by K, which is 0.0556 over up here,
0.4.
plus VTH, which is 0.4. Yeah. Oh, where the hell did it go? Oh no. 2 times the square root of 0.5 milli divided by 0.0556 plus 0.4. And here you get less. Uh-oh. Uh-oh. Did I mess up? 0.5 milliohms K. Did I mess up? This would imply I need 800 volts to do this. E negative, oh, E, oh, thank you. E negative 3 milli. Ah, okay. There we go. Okay, the problem though is what? This voltage on VGS is what? For saturation, it would VG sat would need to be what? 1.2043. Would you guys agree? That's what this calculates. The problem is that that's not possible because the drain voltage is 0.7. So there's no way for me to actually this voltage divider, it's impossible for me to get 1.2 volts here. So am I in saturation?
Oh,
No. Because there's a contradiction that VGS minus VTH is going to be less than VDS. So VDS is 0.7. This is 1.2. Well, this is 1.2043 minus 0.4. This is not true, right? Therefore, not saturation. Would you guys agree?
Yes.
Yeah.
Therefore, I must be what now? I assume.
In linear mode, a triad region.
Yeah, linear or triode. Yep, they're the same word, basically. Triode region. Okay, so now I have a much more annoying equation. K VG V overdrive times VDS minus VDS over 2 squared. Yes?
Mhm.
Okay, so now I want to solve this guy. and I need to find VOV basically. Okay, so VOV will be equal to ID divided by K plus VDS squared plus VDS squared over 2 divided by VDS. Yes, you guys agree?
Yes.
Okay, so I have ID over K VDS plus VDS over 2, and then I get VOV. Okay, and then VGS is just going to be equal to this guy, and then just have to offset by the threshold. Okay. So ID is 0.5 e negative 3 divided by 0.0556 divided by VDS, which is 0.7, plus VDS is 0.7 divided by 2 plus 0.4. Okay. Uh-oh. Wait a fucking second. This also doesn't make sense.
Did you compute
Ah!
one?
I know where I went wrong. No, I don't. Yeah, what were you gonna say? Did we compute what?
Can you see the value of K again, please?
Okay, K is 200 micro times 50 divided by 0.18, 0.556. Is that wrong? 200 micro. Okay. So get rid of the 200 micro, and now I should have amps per volt squared.
Did you divide it by 2?
No, because yeah, no. I keep the 2 here.
Oh, okay.
Did I do my algebra wrong? ID divided by K. ID divided by K plus VDS over 2 squared divided by VDS.
Are you supposed to like just calculate the R1 and R2 values that would make it correct with or within that region?
Well, we have, wait, hold on. First off, did I
Is it the current in series? So
hold on. The current is 0.5 milli plus 55 milli times 2K. And then I do 1.8 minus that. 0.7. Yeah, okay. Okay. Hmm. 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 Hmm.
So when I was looking on Chegg, when they did the current, they did both currents of R1 and R2 plus they did it a different way, to be honest. The way it did it on Chegg, it didn't.
Oh, I have this on check. Do they show VDS equal to 0.7? I just want to confirm some checkpoints.
No, I don't think they did.
Oh, what's their VDS?
Um,
I feel like this should have been saturation.
yeah, let me look it up.
0.5 milliamps times 2 divided by that plus 0.4. That should be good. 1.2 is too high. Is this circuit, does this circuit work? 2K feels, honestly, the VD of 0.7 is to me the weirdest part here. I feel that's a little bit too small. A VDS of 0.7 is a bit too small to be able to do this. So where did I mess up?
From what I see, VD is supposed to be 0.7.
What'd you say?
VD is supposed to be 0.7, apparently.
Oh, according to like an online solution?
Yeah.
Okay, so we're good there. Okay, so then I fucked up either trial or I fucked up either saturation equation. Because one of them is supposed to give me something real, like more something meaningful. Let's see. Oh no. Square root of ID divided by K times 2. Yeah, and then a plus VTH on the other side. Yeah, that makes sense. Okay, yeah, that's too high. Okay. And then the triode region should say triode region should say
Hmm.
VGS minus VT. VGS minus VT. VOV is equal to ID divided by K plus VDS squared divided by 2. And then divide by VDS again. And then answer plus 0.7, 0.4, which is 0.7268. Yeah, okay. And
Okay.
that's not possible to get a voltage divider. Yeah, sorry, yeah, what's up?
No, that's honestly like I'll just wait for the solution sheet. This problem might be just weird.
Can someone send me a solution sheet? There's a chance that they assume saturation, didn't check the work, and I mean it's impossible. Actually, no.
Oh, we don't have it. We won't get it until like.
No, not your professional solution sheet. Whatever online says. What have you guys found?
Oh,
Show-
okay, I'll
show
show
me
you what I
what's-
found. Let's see.
I have a feeling that this problem might be. It feels impossible, or there's a typo. Either the VDD voltage is too low, the 2K is too high, or there's just a lot wrong here. All right, what did this thing say? Let's see. What did you just send me? Your thing said drain current 0.5. Yeah, we got that. Okay, we got that.
Two different solutions, two different ways to do it.
Okay, this is VGS. Okay, oh wait, they got this. This is achievable. This is achievable. This is 0.4. Okay, VTH 0.4. Okay, that's okay. VGS minus VTH squared, 50 over that, 200 micro. And this is ID times 2. So when they solve this guy, okay, so for some reason, oh, I am stupid, guys. Oi, oi. Who let me do the square root? Who let me do the square root in ID, but not these guys? Oi. My God. My God, I'm bad at it. All right, we do this guy. It's the square root of 2 times 0.5 e negative 3 divided by k 0.0556. Yeah, plus 0.4. Hey, oh my God, I am bad at algebra. All right, I'll leave this here. This is possible. Okay, so now we have a VG. Now we want a VG to be equal to 0.5341, and the voltage divider is 14K. Starting in the total resistance. So the total resistance is going to be 14K, and I want this voltage here to be 0.5341. Okay. Meanwhile, the sum, the total resistance is 14K. And I want this voltage here to be 0.7, and that establishes, this is enough information to establish R1 and R2. So all I need to say is that R2 divided by the total is equal to the fraction over the whole. And I know that this side is equal to 14K. So I can just solve this guy. I could solve that R2 is equal to 0.5341 divided by 0.7 times 14K. So therefore R2 is equal to 10.68. And therefore R1 has to be equal to the remainder that adds up to 14K. 3.318K. Okay?
I see.
Yeah, is this okay? Or yeah, does this make sense to you guys? How we did this problem? Sorry, I messed
Yeah.
up so bad.
Oh, I think Ron posted the solutions. The teacher solutions.
I just posted one. Yeah.
Oh, are we
Yeah,
correct? 1.8.
Can I see the answers?
Oh wait, my answer or this answer?
Oh no, yours.
I disagree. Wait, whoa. What the fuck? Why they do that? Nah, dude. I disagree. KVL here, man. Right? We agree this is fundamentally broken. 0.5 goes down this way. 0.05 goes down this way, and that's all KCLCs, right?
Yep.
This should not. I think this is wrong here.
Looks like that's wrong, right? You
Yeah,
should
right?
5 plus 0.05 because that's the only current that flowing through the
Yeah,
R1.
exactly. You're doing KCL at this node here. Agreed? So
Yep.
KCL, there's only
Yeah.
one input current and two output currents. And the two output currents is 0.5 and 0.05. And the input current is whatever we're solving for. Right? Yeah?
Yeah.
Yeah.
Okay, yeah.
That's
I do not agree with this solution.
Wait, is that 17.7?
Where?
Yeah, I just found two
Yeah.
random solutions.
Oh, that's not the solution I sent.
Oh,
It's in
no.
notes and resources.
Yeah, it's in. He sent the actual teacher's solutions.
Oh,
Yeah.
Yeah, that's
geez.
that's wrong. I just found like two references off each other.
sorry, I copied the wrong name.
Yeah,
Oh,
I would not rely on those ones.
It's
I
in
didn't
the,
know we had the
section.
solutions from the teacher.
okay. Oh, what is it?
the most recent one in the notes and resources.
Yeah, no, but what's the question? 17.7, yeah?
17.7, yeah.
VGS 0.5, VGS 0.534. That matches 0.5341. Yeah, okay. 3.317, 10.683. Yeah.
Yeah.
Okay. Are we good here?
Yes.
Yeah.
Okay. Sorry that took so long.
Oh,
Okay.
appreciate
You
it.
guess probably want to see a small signal question, right?
Yes,
Yeah.
please.
How much time do you have? Like you're good,
I
right?
am now not gonna. I mean, okay. I have another tutoring session from 8 to 10 p.m. today, so I was trying to get myself some dinner.
Okay. Yeah. Do you want to just like, if you have time, then yeah. Otherwise, like,
I'll cook something real quick on the side. I mean, afterwards. I don't know. Maybe I'll postpone my next tutoring. I'm tutoring the guys in EE 110 next.
Oh.
So
nice.
you guys, if you guys are free to join that.
You
want
gotta
to-
study
no.
for 124.
Yeah, I know,
I
right?
studied so much for that. I'm done.
Yeah. Well, no. Bodhi plots report, man. I want you guys successful. Okay, so where are we at?
Wait, Eric, yeah, I'm new to you. I mean, you are new to me, but how did you guys find you?
How'd I? Oh, I'm a friend of
He's
mine
good
went to
for
San
that.
Jose State
Oh, okay.
during COVID. He's since graduated and he's in the field now, but it's now become almost tradition. I heard that the SJSU people were not
I just want to
professors. Some of them
personally thank you.
some of them struggled. So yeah, yeah, I think so, a few of your alumni basically
Thank you.
yeah.
Yeah,
Okay,
he helped me last semester.
yeah. I just like the material, man.
Oh, this is great.
Yeah, like I said, if at any point the material is non-interesting, or I make it like oh god. Can I find the small signal model? Wait, sorry guys. Oh, found it. Wait, sorry. Which problem? Quickly? 6 point, which one? You guys want to do 2.8?
17.28.
Yeah,
Okay.
28.
Oh, there's freaking one. Oh,
Okay. So there's a few things we have to prove here. There's a few things we have to prove here. So let me just do C for you guys. Oh. Let me do C for you guys. So in this problem, what I want you guys to identify is that there's three key sections. There is, first off, identify the signal path. you see input, it goes from here, then where? Where does it go? Where does it have to jump to next to head towards the output?
Goes to
Towards drain.
M2
Which way?
up.
Don't say up or down. Tell me the the node.
Drain
Oh.
source.
That's the drain.
That's the drain.
I mean source. No, drain is the lower potential, and the source has to be the higher potential.
Ooh, that's incorrect,
Oh,
Tolede.
that's
Wait,
incorrect.
other way around.
Other way
Yeah,
around.
this is the
Yeah,
source.
sorry,
this
sorry,
is the
yeah.
drain.
So drain
Right.
after common.
I hop up, I go up, and am I at the output?
Yes, that way.
Good. So we're home free. Good. So here is one block. Here is the other block. And here is another block. Okay. So are you guys familiar with common source, common gate, common drain amplifiers? You guys know what that means when I say that or no?
Yes, kind
Just
of.
common source and gate.
Kind of.
Kind of.
Okay, that's fine. So there is
Need some clarification.
honestly, oh god, are you guys gonna get tested on this? What does this homework do?
Oh yeah, no, we're good. The homework's good. It's due today, but like this is what I was mentioning earlier we were talking in the beginning about the topology and
Yeah, okay. So here's the cheat sheet.
Yeah.
But you want more intuitive explanation? Or I can show you how to use the cheat sheet.
Show us how to use the cheat sheet.
Okay. Here.
I'm putting that in my notes.
Alright. Here's the
Well,
cheat
you
sheet.
can have the cheat sheet, but not knowing how to use it, that would screw you on the.
Yeah, for sure.
All right. So basically every single time the signal, so
Yes.
you see how this guy goes in through here and goes out in through the gate and out through the drain, yes?
Yeah,
So what does it not touch?
the source.
So what do you call this? Common source. Got it?
Yeah.
Wait, as simple as that?
Yes?
Oh wow.
Okay, next question. Suppose my input is suppose I have a MOSFET and the input is the gate and the output is the source. What do you call this?
Common source.
Common drain.
Common drain, correct.
Oh, common source. Okay, I got it.
Suppose my
The
input.
opposite follows, right?
No, it's the one that you don't, it's the leg you don't touch.
Yeah.
Suppose my input is to the source and my output is to the drain.
Common gate.
What leg do I not touch?
Common gate.
Gate, so it'll be common gate.
Correct.
Man, this is so much easier to
Wow.
remember than the way he taught it.
Next question. Can that input, can I ever, can I input signals onto the gate? Can I input signals onto the gate? Is that allowed?
On which one?
It's in the gate.
In general,
Yes.
Well, we just put a small.
Yes.
it is possible
Yes.
to input to the gate. I am allowed to perturb VGS is allowed to be perturbed. So basically my inputs are either VGS or my inputs are either VGS. Am I allowed to input into the source?
Yes.
Yes, I can. Am I allowed to input into the drain?
Not sure. No, maybe.
You are not allowed to input to the drain. Can you output from the gate?
No.
No.
Can you input? Can you output from the drain?
Yes.
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 Here's an example. Can you output from the source?
No.
No.
Huh?
Oh.
Oh yes, yes, you can.
Yeah.
The source is the joker. You can only input gate and you can only output drain. So if I drew this and you see if I see that input on the source is this, what's the only configuration I can do? Where does the output have to be?
You're saying that's the input, right?
Source?
The
So
gate.
we will have to
Of the
be
drain.
Drain.
What's the only legal option left?
From the drain.
Okay, and this is therefore
Common gate.
good.
Okay, that makes sense because it didn't touch the.
If I tell you guys that your output, if your source is outputting, what does this have to be configured to be?
It should be from the gate. the input should be from the gate.
Correct. Therefore, what's the configuration?
Common drain.
Correct. Any questions?
Nope.
These are the only three legal configurations. So if I say, another way I could test you guys is if I say common source, where's the input, where's the output? It goes from where to where?
Input is gate and output is drain.
Good. If I say common gate, where's the input and where's the output?
Input is source and output's drain.
Good. Next, if I say common gate, oh sorry, if I say common if I say common drain,
So input is the source.
and then output is
Uh,
The
gate
is that allowed?
is not allowed.
Okay, try again.
So gate should be the input, and then output should be source.
Correct. That's it. You guys solved all three. Those are only three topologies. Okay.
Amazing.
Amazing. Good. So you guys see what I say? Common source, common drain, common gate. Any questions? Input, output, blah, blah, blah.
No.
All right. So you have this section of the table done. Next, next we're gonna talk about also, by the way, common drain is sometimes called source follower. This one has a special name. I don't know why they like that. Sorry. We can explain source follower, but common source, common drain, common gate. Okay, these are the rules of the game. You can see the gate can only be input. The drain can only be output. The source can be what is the jack is a jack and could be either one. Do you guys have any questions about the type of three types of topologies? Or are we can we move forward?
Can move forward.
All right, perfect. Now, in this amplifier scheme, the input touches this and goes to the output. It's common source. Does M3, does the green box have a sense of input output?
Wait,
No.
say that one more time.
It
Does
doesn't
the
have-
green, does the signal path from input to output have to go
It
through
looks
M3?
like it doesn't, but
It does not go through it. Therefore, there is no common source gate or drain topology associated with it.
is that because of the resistance?
No.
Is that
no.
why you can essentially, like,
I will show you guys how to treat it. No, I'm saying that this is no topologies listed here. Similarly, there's no
I see, I
topology
see.
listed here either.
Yeah.
Got it? But what are these? This device actually touches the signal chain, but you can see in M3, it's just a impedance. It's just from what it dangles off like an ornament and it goes to ground. Yes?
So that signal goes to V out. The reason why we say it doesn't touch M3 or M2 because of the impedance, the high impedance of both of them. So
No. It's not that high impedance. The signal chain just does not go from its drain to gate to source.
Oh.
Remember, the definition of no, you cannot ignore it. The definition, I'm just trying to identify when do you have to apply common source, common drain, common gate. It's when there's an actual idea of input output. Here, the input signal has nothing to do but to go in here and then output here, right? So
Oh,
did
I
it go
see, I
for,
see.
did it do a jump? At no point here do I have to jump from here to here to here,
Got it.
right?
Mm-hmm.
Or if
Got
jump
it.
from, or the signal does not magically come from here and then jump up, right? Similarly, I do not go from here to jump here to out here, right?
Okay.
I do not go through the boxes.
Yeah, I got it.
Okay. So then the question is, what the hell do the other guys do? Okay. So you need to, so here's what you have to do. Okay. Input. So what's the input for a common source? Let's focus on common source. For a common source amplifier, what's the input? It's located at which portion?
At the gate,
At the gate. And looking into the gate, what's the impedance into the gate?
very, very high.
It's infinite. There's no current flowing into it, right? Therefore, it's infinite impedance. Okay? That's so no current. Easy. The output impedance. What is the output? It's the
Yeah,
Right.
can you go slow on that one because that's why I'm getting confused on the output.
no. It's okay. It's okay. I'll define what I mean by impedance, but do you see what it mean? What this mean? Like the output is drain, and this is what it is.
Yeah.
In this table, let's pattern match. Gate, whenever there's really not Z in, Z out, just call it like these two are ZG.
Yeah,
This is ZD, and this is the exact same expression as down here. Both of these guys are the impedance into the gate. and this is ZS, the impedance into the source.
Yeah.
Okay, so I'll define what these mean. So I know I put like six things, but there's only really three equations here. Infinite, RS, or RD. You got it?
Yeah.
Okay. So how does this work? Okay. So effectively, if I have to move from here to here, or sorry, if let's consider M3. M3 is a device dangling off V out to ground, right? So if I just copy this guy over, what is this guy look like in small signal? Right? So it's connected like this inside, right? But what does this guy look like from the outside? From these two terminals? What does this guy look like? And you guys agree what I'm trying to do here? I'm putting it inside a box and I'm trying to figure out what the impedance of that box is.
So you,
What do
you
I mean
mean
by impedance? What do I mean by impedance? Impedance means for any two terminal device, I could figure out a VX-IX combination such that, and the ratio of VX over IX determines the impedance of it. It's like a resistor, right? And I could put in any test box inside this. Any circuit I could put inside this, and I could find its impedance. Yes?
Are we looking into the input impedance from the positive side or from the gate side or from?
Well, no. See, I hate how they drew it. Imagine you could redraw this guy such that the black
Yeah.
line connects here,
Yep.
right?
Mhm.
So are you able to draw a box such that there's only two terminals piercing through the box?
Would that terminal be one terminal? Be
No, it's a two. This is a two terminal device.
Two terminal, one is
Oh,
on
I
the
see. But
Yeah.
but that node at the top is just one node, right? Because they're connected now.
Yeah. It's one node. I know. I hate how I drew it. I would have preferred if they drew it like that. Would have made my life easier.
Okay.
Yes. Does that make sense?
Yeah.
So in here, I have basically this device.
Yeah.
Yes. You guys agree?
Yeah.
I have this NMOS device. And because I drew a box, any box that is only pierced twice, 1, 2, has an equivalent impedance. You got it?
Yeah.
All right, let's figure out what the impedance is. Okay, what's the small signal model of any MOSFET? Gate, source, drain. Yes? I have a resistor R naught, and I have a
Current source.
a GM VGS. Yes?
yes.
And here's VGS here. Yes?
Yeah.
And I know in this device, this device is also connected like this. The gate and the drain are the same connection. Yes? The gate and the drain are connected to one another.
Yeah.
Okay? So I want to find the impedance of this guy, right? And I'm just applying, externally, I'm applying a test circuit VX, and I want to know the IX that flows because of that VX. And the ratio of it gets me the impedance. You guys agree? You guys agree how to test impedances?
Sorry, can you repeat that again, please? Okay.
Sure. If I want to figure out if inside this box, I want to figure out what's the impedance of a resistor. What do? I apply a VX and an IX. Yes. And the IX. Okay. And then I solve the circuit. So I have VX is equal to RIX. The ratio of VX to IX is the impedance of what's inside. And would you agree that what's inside the box is an R?
Yes.
Okay. That's basically what we're doing. I applied two test signals and I had to find the ratio of the two to find the impedance. Does that make sense?
Yeah.
Yeah.
Okay, so let's do it. So I apply this ratio, right? So, well, I have this circuit now. I have a circuit where I have a VX applied with an IX, and I'm going into a circuit that looks like this. It has a dependent current source going down, and it has a resistor, R naught. And this is GM VGS, but VGS is also just what? It's just the VX being applied to it, isn't it? VGS is VX. Would you guys agree?
Yeah.
That's the V that we're applying, right? So
Yeah,
since
the VX that we're applying. And here, if I said, hey, what's the resistance of these two? You guys would just tell me it's the parallel combination, right? So this is R naught, and this is what? What's the impedance of this
One
guy?
over- 1/GM.
Yes, because here, let me explain why. So what's basically what's Ix equal to? Ix is equal to GM Vx plus Vx over Ro from KCL here. Yes?
Yeah.
Okay. Vx divided by Ix is equal to what? Vx divided by Ix. So I factor out Vx. I now do the math it takes to get me the ratio. So here's GM plus 1 over Ro, yeah? And then Vx divided by Ix is equal to 1 over 1 divided by GM plus 1 over Ro. Which
Right,
I could
right.
rewrite this guy as 1 over Ro and 1 divided by 1 over GM, which is the definition of parallel, isn't it? The inverse of inverse impedances is the definition of parallel. So this is equivalent to 1 over GM parallel Ro.
Right.
So what's the impedance? So when I have this connection from whenever the gate and the drain are directly connected, it's called diode connected.
Oh, right. It says that in the notes.
This is
right?
called diode connected. And what's the impedance of a diode connected? And a MOSFET is a 3-terminal device. But if I short 2 of the terminals, how many terminals are left?
2.
One.
And any two, no, whoa.
Well, you said you short 2 of the terminals, right?
Yes, I have 3 terminals and I short 2. How many terminals are like? This guy is now effectively a
The
2-terminal
2
device.
become 1 and the last one, so you have 2, right?
Yes.
No,
Oh, when I say left, I don't mean like the dangling source. I mean like, if once I short these 2, how many terminals does this guy actually have?
2 terminals. Because
2, right?
Yeah.
Any 2-terminal device, a capacitor is a 2-terminal device, a resistor is a 2-terminal device, an inductor is a 2-terminal device.
Yeah,
We treat it as a resistor or impedance.
Every single one of these guys has an impedance. Agreed?
right.
Yes.
So can a diode connected device. And what's the impedance of a diode connected device?
1 over GM parallel or not?
Or not? Correct. And that's why I say this. Yes.
Yes. Okay, makes sense.
Right.
So
Okay,
one question.
So my next step for the circuit is that I can just replace this guy with what?
1
A
over GM parallel to R naught.
correct. Just a resistor with what resistance? RO parallel 1 over GM. Yeah.
Yeah.
And you subscript. This was MOSFET number 3, right? So you subscript. 3. You guys got it?
Yeah. That makes so much more
Yeah.
sense.
What about this guy? This guy is a PMOS or an NMOS?
It's a PMOS?
It's
PMOS
a
going
PMOS,
into,
correct? Because the arrow points in. This is source. This is gate. This is drain. Yes.
A quick
Yes.
question, Eric.
Yes.
Yeah, I got confused earlier when I said source was the higher potential and the drain was lower potential. From the lecture,
That's PMOS. That's PMOS.
That's for PMOS, right?
Correct.
But for NMOS, all the way around.
Source is lower potential.
Got it.
Because the carriers are electrons on NMOS. and
Yeah.
carriers-
Okay, got it.
Right.
Thank you.
Okay. So for diode connections, it's just a fucking resistor. What about this? Well, what impedance am I looking into? This guy is a 2-terminal device, right? VB is not part of the signal chain. VB
Yeah.
is not part. It's just a bias voltage. So this is AC grounded. Yeah.
Yeah.
So what is this guy?
It's
This guy
just
has what
resistor.
impedance? Or sorry, this guy is, I'm looking from the circuits, from the signal path perspective, what I want to replace this guy with the impedance looking into this way, right?
Mhm.
So which device am I looking into? Which terminal?
Drain.
The D.
Right.
The drain. So I take my Z and D expression and I figure out what this guy needs to be. In my general expression, RD, in my general my reference schematic, my RD is just any resistor that's also attached to the drain. So from this guy's perspective, it's like whatever resistance is also dangling here. If there's a resistor here, it would have been in parallel. Would you agree?
Yeah.
So in my expression, typically you could kind of just ignore this. There is nothing in parallel, so it's infinite, right? This is an infinite resistor. So you could just kind of ignore that. So this is the key section. Okay. So then and RS is the source resistance. RS is the source resistance. And what is RS for this guy? what is the impedance from the source to ground?
Storage to-
What is RS here? Is there a resistor from source to ground?
No,
No.
Okay, so what's the resistance of that?
Zero.
0.
0, right? Good. So R is equal to 0. For my expressions, R is equal to 0. So what's the and RD is there's nothing really in parallel, or technically this is in parallel to this. Like you see how this is a component from here, from this V out net to ground, and this is from V out net to ground. So this is in parallel with this. So whatever. But you could, to be honest, you could kind of ignore the RD, or you like this parallel expression is just helping you reconsider the fact that there could be resistance in parallel. Don't ignore them, but I don't think you guys will. So RD for now we just assume is for this box is infinite. There's no RD attachment anywhere. So what's the ZD for this guy? ZD is equal to infinite in parallel with R naught 2 plus RS is equal to 0 times 1 plus GM 2 R naught 2. So what does this guy simplify down to?
R naught 2.
R naught 2. Good. Let's prove it. So this guy is what? You have a gate, you have a gate, you have a drain. You have a gate, you have a drain, you have a source, yeah? Like this. And they're saying that the V gate is grounded, right? VB is just a bias voltage. So in the AC world, it doesn't have any perturbation. There's no perturbation, so it's just a grounded signal.
Yep.
Okay, drain is grounded as well. There's no source resistance. And here's sorry, drain is exposed. I'm looking into it. I'm trying to apply my test voltage into it, my VXIX into it, and my source is grounded. You guys agree?
Yeah.
Okay. So I'm just trying to find, and so if I'm trying to find the p into this, if VG, what is VGS here? If the gate is if the gate is AC grounded and the source is AC grounded, what's VGS?
0.
0. So if VGS is 0, what's this guy become? It's GM VGS, which is equal to 0. If a current is 0, what does it look like?
Current is 0.
0 current looks like what component?
It looks like
Open circuit.
Open circuit, correct? So then the only component left from this guy is what?
the resistor.
VIX.
And what did we get?
That's the R naught 2.
You guys agree?
Parallel with
Which
Yes.
Yes. So so what does this blue box become now?
Just a resistor with R naught in resistance.
Correct. Any questions here? So now we have now we simplify those two blocks, and I just need to figure out what the common source gain is, right? This is just one common source stage. So I go to my cheat sheet, I go to common source, I take this guy, and I copy it down. Okay, so which MOSFET am I going through right now? I'm going through M1, right? So this is so the voltage gain for this stage is R01, 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 GM1, and GM1. Just make sure you subscript to respect the 1, okay? So AV here is GM1, RD. So what's the total resistance seen by the drain? So here's the drain. What's the impedance if it peaks out? What do you see?
R naught 2.
Yes. What else?
R naught 3.
And 1 GM3.
parallel.
Everything parallel. So yeah.
Yeah.
Okay. That's RD, right? Parallel R01. Parallel. Is there any RS?
No.
No.
RS is grounded here, and this RS is equal to 0, right? If R is equal to 0, this whole term becomes
Infinity.
infinity. Okay, and what's that? So what do you guys get?
Just
Negative GM1 R naught 2 in parallel with R naught 3 in parallel with 1 over GM3 in parallel with R naught. That's the answer. Any questions?
That's pretty intuitive. Sure.
Yeah.
I would.
I have a question when you consider the diode.
Yes.
So we were connecting that thing with the gate, right? So
Wi-
will that
Not
make
connected.
any difference when it is like connected to the ground?
What, when gates connect to the ground?
Yeah.
Didn't we not just do that?
No, in M3, isn't it? It's the same thing, right?
No, if
The-
if M3 is grounded, right? If the gate was grounded
It'd
or
be like
AC
this.
grounded, is
That
what
would-
you're looking
It'd be
into the drain,
similar
right?
to the other
Yeah.
one.
So what's the P? But look at this
In the
guy.
middle is the same thing, right? Yeah, the blue box one.
Okay, then here to make sure you understand what I'm saying. If let's pretend the gate was AC grounded and not connected. What's the impedance looking into the green box?
So R not just R03 for that one.
Anything else?
No,
Correct. Just want to make sure you're confident.
Yeah.
Yes,
because that looks like the blue box one. Because
correct.
okay.
Okay, does that make sense, guys?
Can we add a source resistance in this equation and then solve for it?
Yes, of course we can add a source resistance into
So
one.
that we will cover like every topic, I think, because I don't think we have much time to
Wait,
go
do you
over.
want do you want the common source do you want the amplifying stage to have that, or do you want one of the impedances to have it? Oh, here. I'll just make up a question for you guys, actually, real quick, okay? I'll make up a question and I'll show you guys how I solve it. Yeah, okay, so here. Suppose you have this, right? I have this guy, it's a NMOS. This guy's a nice NMOS device. I go here. Go here. I go here. I have this, 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 this.
Oh, that was like a test
This,
question.
this. We do this, do this, do this, do this, do this.
Everything is a diode connection then.
BB, V bias. And I call this V out, and I call this V in. Okay, any questions? And let's call it M1, M2, M3, M4, M5. Okay. Which one's carrying? Where's the main signal path going through? Which FET?
M1,
M1.
And what type of state? What type of
NMOS.
NMOS.
configuration? Damn it!
Oh,
Common source.
Good, common source. Yeah. Okay, so I know it's a common source stage, and that's it. It's just one common source stage. Okay. What happens to 2, 3, 4, and 5?
2, 3, and 4 looks like the diode to me.
Yeah,
Okay,
but
they're all
it's-
diode connected, so they're just two terminal devices, aren't they?
Yeah.
Okay,
And then you got
then-
one resistor at the bottom.
Yeah.
and this guy looks like it's gonna be kind of a V bias with just a resistance, right?
Yeah,
So do you see how each box is pure? Each box only has two terminals, yes?
yes,
Okay, so I could redraw this. I could redraw the circuit as the M3 becomes what? A resistor with R03 power 1 over GM3. Yeah.
yeah.
What about the other one?
MR02 parallel
Mhm.
1 over ZM2
Why? Why is it like this again? Because the circuit is
to
what? What's the key word? I'm looking for a key word.
Diode connect.
Diode connected. Correct. Okay. Then the circuit goes down to the drain. Then over here, what does M4 look like?
the same diode connector.
So tell me explicitly the impedances.
R04 parallel to 1 over ZR4.
GM4. Continue. What about the bottom?
That's just R5, R05.
Or not 5. Good. To ground. Also to AC ground. Good. Then we have this common source stage, right? Okay. If I take the common source stage, right, and I go this guy, right?
Mhm.
I take this guy. Here's the equation I derived for you guys. The proofs, you're going to explore it. Okay. So it's equal to negative GM1. If this is M1 in parallel with whatever the drain will see. So what impedance does the drain see? It sees this guy
And the donor
in
guy.
series, and it sees this guy in series. Yes.
Yeah,
So it sees R naught 3 parallel 1 over GM3 plus R naught 2 parallel 1 over GM2. That's one resistor. That's the purple resistor. In parallel to
Double bar.
the purple one, or the dark blue one, whatever. R04 in parallel with 1 over GM4 plus R naught 5. Yeah. Right. And now that's all of RD. And then I need to now, so that's RD substituted in. Now I need to put this in parallel with R naught 1. And then RS is 0 here, right? It's a short circuit, so RS is equal to 0. And therefore it's parallel to infinity. So your answer is just this. Any questions?
No questions.
No.
No, not for this question.
Not for this fake question that we just made up. But yeah, I just showed you could also put them in series, which you guys probably will see shortly. Okay, so what type of question do you guys want to see now? You want to put a source resistor?
Oh, I have
Yes.
one question regarding the small signal analysis. You've
Yes.
done one for NMOS, but what would the PMOS look like?
PMOS you draw the exact same thing. What do I mean by that? So what does a small signal model for NMOS look like? NMOS, there's a gate, there's a drain, there's a source, yes?
Yes.
Is there any connection from gate to source? Okay, but I call this VGS, yes? And then there's two components from the drain, right? There's a resistor, yeah? And I call it R naught. And there's also a current source that points which way?
Down.
Down.
No, don't say down, from where to where?
Oh,
Drain the source.
Drain to source.
Drain to source, and I label it GM
PZS.
VGS, good. Okay, if I switch the N to a P, it's the same thing. All right, any questions?
It's literally the same thing.
Yes, you draw it the exact same way.
Oh,
You label this the way it is labeled. You got it? For example, if I wanted to do this and I put a PMOS device here, right? And I call this VG and I call this like VRD and this is whatever, right? If I had this, where's the source? Here, the drain's here, and the gate's here, yes? When I draw this device, this guy's AC grounded, so then this is what I do. I literally just draw this guy. I literally just draw the guy. And I have to, and if I want to draw it the same way as this, right? Where does this, so some people might draw it upside down. I hate doing that shit. I just still draw it right side up. Like some people put the drain here and put the source here. Because they think it'll be easier to map it, right? Don't do it. Put the drain up here, put the source down here, put the gate here. The source, just think about, do component by component. The MOSFET model is exactly the same. The arrow points from drain to source. The arrow points from drain to source. And the VGS goes from VG to S. Okay? Then, so this is now a PMOS device, but the key here is that because we didn't flip it, you have to be careful when you connect it. The source connects to ground. The drain connects to a RD to ground. And the VG goes to VN or some VG, whatever, right? And this is also a PMOS. In other words, I'm encouraging, even though it's drawn like this, don't actually draw VG and D, GDS in that order, like in that in the upside down
Practically
configuration.
Draw the same and then go back to the original drawing and then pick up with a BN and
Yes. So think about what, draw all the connections to the gate, draw all the connections to the drain, draw all the connections to the sources. Okay?
okay, that makes sense. Thank you.
Okay, basically draw inside the MOSFET box. The MOSFET box is how many terminals? 3 terminals, right? Inside the box, you draw the exact fucking same thing. Outside the box, you connect them one at a time. Got it? Yeah?
Wait, so
Dude,
inside
mind blown.
you draw the same thing. Outside, you connect them one at a time.
Yeah.
Okay. Makes sense.
So there is no difference between PMOS and NMOS small signal. It's the same thing.
Gotcha. I thought we had to like
No,
flip it and stuff.
no. I mean, you could flip it, then you flip again, then you flip again. It turns out you flip once, but then the math flips it again. technically, if you want to draw the PMOS device as per defined, right, per the physics of like where electrons flow, you will draw upside down, but with a negative somewhere. If you negate, but then if you distribute the negative, you will get back the original device. So I'm just giving you the conclusion. Technically, it's a times minus one in the math, but to you, it's the same, right?
Yes,
So I'm just telling you, it's the same.
I got, okay, that makes sense. That makes sense. Thank you.
Yeah, I know you guys inherit with you. Isn't it different? Yeah, it is different, but it's also different twice. So it cancels.
Right, this makes more sense and it's easier to understand.
Yes, I'm trying to minimize the amount of stuff you need to memorize.
Thank you.
Okay. Any other questions?
I think I'm good.
Me too.
Okay.
Yeah, I think it's time you took a break.
Yeah. And so, well, technically, we didn't answer the part 2 of this, right?
There's a
You guys want to, you guys want to see this shit, right?
Oh, that's
Here.
I would like to see more complicated one, which is on.
That's-
This is complicated
is
because I'm
really
telling you straight up,
complicated.
this one is complicated because look, it's not dial connected anymore, right? Because the gate is not shorted to the drain.
Yes.
So this is actually not, this is one actually you need to solve. Again, this is not in the cheat sheet.
yeah.
My point was there is one more like a problem like this, which is not connected on the like diode connected.
This is
but
the same one I
similar.
think.
You can look at
Next one over.
17.32b. Like that's more.
Wait, so you don't want to do this one or you want to go try another one?
If you have time,
No,
Ian,
do it.
please. This is like this
All
was
right. I'm moving the connection up. You guys see? Just so that the boxes I draw are easier, right?
Yeah.
Right? So don't, yeah. So yeah, okay. But it's the same, it just so it fits that idea of like, 2 terminals. Yeah. Okay. So the bottom one is what type of amplifier? Or configuration?
And Moss and this goes.
Common source and MOS.
Good. It's a common source here. So it has, so because it's common source, it has this gain. Okay, so the final gain is this. And I have GM1, I have R01, I have R01, R01, GM1. I just need to know what is RD and I need to know what is RS. For this case, what is RS equal to?
0.
0, because it's a short, right? And I just need to figure out what RD is. So RD is whatever comes up here. So I need to figure out what the impedance of this top block is, right? All right, so let's figure out what RD is. Okay, so from here, I need to figure out the impedance of this 2-block network. Okay, so I put in this guy's a PMOS. I put this guy upside down. And it goes apply the voltage this way to get the current flowing into it this way, into the drain. Okay, so it's a bit upside down, but we can flip it. Okay, so let's draw the small signal model. So I'm going to flip it right back up. Here's Vx with an Ix going into something. And what's it going into? It's going into a,
Or load. Or RD.
RD.
it's going into an RD. And the RD is this is now the drain. From the RD, there's an R naught here. And there's also a 1 over G, the GM, VGS here, yes?
BGX.
Yeah, VGS, right? And then the source is grounded. So it loops all the way back around, yes? Like this is a complete circuit, right? So that's VGS, but VGS is also equal to what? It's VGS is also equal to Vx. Would you guys agree? In this problem, the voltage applied across the whole device is the VGS because of how this gate is connected after above the resistor. You guys agree that this is the gate?
Yeah.
Okay. So I need to find the impedance of this guy. Okay, so we use I like to use KCL for this one. So the current going into this guy is going to be equal to Vx minus this VD, right? This is Vx minus VD divided by RD. That's one current. That's the current going through this guy. The current is also equal to VD over R naught plus GMVX. You guys agree? There's two ways. The current is either equal to this guy or it's equal to this guy. Added up.
Yes.
Okay, and I just need to find, and my goal is to find Vx over Ix to find the impedance of this guy. I'm trying to find Zx. Okay. So I have VD here and I don't like VD here. So let's try to figure out how VD can go away. So I'm going to use this guy to solve for VD. So VD is equal to VD is equal to the Vx minus IXRD. Yes, you guys agree? Times RD this way, bring this guy over, bring this guy back. Okay, that's one expression. And then I can now substitute this guy into here. And now I have Vx minus IXRD divided by R naught plus GM Vx is equal to Ix. Would you guys agree?
Yes.
Okay. Okay, so then I bring Ix over and I factor, I have 1 plus, and then this is now what? This is RD over R naught is equal to Vx, and then this factor is 1 over RO plus GM. Okay. Vx over Ix, therefore, is now equal to, Vx over Ix is equal to 1 plus RD over RO divided by 1 over RO plus GM. And I'm going to rewrite that I'm going to rewrite the denominator as this 1 over RO plus 1 over GM, just a double inversion. This bottom guy becomes R naught in parallel with 1 over GM. And then I multiply this guy out by 1 plus RD over R naught. You guys have any questions here? So this is like a scaling fact. This is like, in other words, it is this guy basically has the impedance of a regular diode, a Z diode connected, right? But it has an extra bonus. It has an extra bonus factor of this. Does this make sense?
Yeah.
This is just a unitless term. That's just some extra bonus factor of RD over R naught. Correct? Or do you guys agree?
Yes.
Okay, and that's what this guy is. Okay, so then I can redraw this guy basically. I can redraw this guy. By just deleting this. And I'll just say that it's a resistor with R naught 2 in parallel 1 over GM2 multiplied by this extra scaling factor RD over R naught 2. Yes? Is this okay?
Yep.
And then so therefore that's what RD is equal to. It's R naught 2 parallel 1 over GM2 times this bonus factor. 1 plus RD over R naught 2. And then we just solve for AV now. So AV is equal to 1 over GM, RD goes in here, R naught and RS is 0, so this goes to infinity. And we're done. You guys have any questions?
I'm good.
Yep, here's your answer. Any questions?
No, I think we're good.
Okay, now there's, I think you guys had one more, right? Well,
I mean,
which
like
one was
that's in that question. Like we have added a diode under is a
Which
resistor.
one? Which question?
There, yeah, that one.
Which one? A or
Diode
B?
connected.
Yeah, diode connected. Yeah, that one.
Oh, which one? A or B? Damn it.
D.
Okay. Jesus. Okay. Okay.
It's basically
Okay.
the same thing. Just it's like
Okay.
diode.
You see this? You see it's VN? Okay. So then M1 is getting run over, right? So I go through here to output, right? Agreed?
Yeah.
What type of configuration is it?
NMOS.
Damn it.
Common
Configuration.
source.
Common source.
There we go. Common source, yeah. Common source amplifier, okay. At the bottom, I have a green box, yeah. And at the top, I have a
The same.
Blue
Yeah,
bar,
it's-
yeah,
I'm just gonna call it, what?
whatever, I don't know. Okay, what's the gate? Okay, so the bottom can be replaced with what? A resistor that has what resistance?
R03 parallel with
One over
ZM3.
GM3.
Yeah,
Okay, and the blue?
it's the upper one. That we
R,
just right.
One we just saw.
R02,
Parallel 1 over ZM2 plus 1 over RD over
RD
R.
over,
Yeah.
Oh, alright, sorry, okay, I memorized, sorry, my bad, okay, yeah, remember? RD over R dot, yeah?
Yep.
Okay, and then I have a common source term, right? Okay. So the answer is gonna be, and this is, I'm gonna call it ZD, and this is gonna be the ZS of it, yeah?
yeah,
Or sorry, this is the ZD for the common source, and this is the ZS of the common source. So the voltage gain is equal to negative GM1 for the MOSFET 1 times RD, which is this thing.
We can say that is a GD or RD.
Parallel R not 1. Right? R not 1 inside here, parallel with this shit. Okay, so parallel with RD, which is this shit. Divided by this shit. Times R not 1 over R plus 1 plus GM1 R not 1. Okay, any questions?
did that so easily.
Literally.
I mean, that's the power of the cheat sheet.
Oh.
Because I pre-solved the generic circuit for you.
Yeah.
Everything is pre-solved here.
Oh my god.
I'm
This is,
copying that.
yeah, no, for sure. Thanks for teaching us how to use it.
Yeah.
Thank you, thank you.
Yeah, thanks a lot.
Actually, I'm gonna use it now.
All right. Well,
All right,
let's
thank
end
you,
let's
Eric.
end the recording there.
Awesome.